The paper we're breaking down today is titled Causal Forcing, Autoregressive Diffusion Distillation Done Right for High-Quality Real-Time Interactive Video Generation by Hongzhou and colleagues.
And this one is a big deal if you're in the generative video space.
Yeah.
It really tackles this massive architectural gap we see in real-time video generation.
Right. The problem being, why does it always end up a blurry mess when you try to distill a big, powerful video model into something fast and interactive?
Exactly. And the core insight here is something called frame-level injectivity, or, well, the violation of it.
Okay, so the old methods were basically asking a student model to predict one specific clean frame from noise. But the teacher model, because it can see the future, knows there are actually multiple possibilities.
Right. And because this student can't see the future, it sees a one-to-many mapping. So what does it do? It just averages all the possibilities.
Which gives you that blurry, washed-out look.
Yep. The solution they propose is causal forcing. It's a three-step pipeline. First, train an autoregressive teacher with teacher forcing. Then do a causal ODE distillation. And finally, you polish it up with asymmetric DMD.
And the number are frankly pretty wild. It beats the previous state-of-the-art by, 19.3% in dynamic degree?
And 16.7% in instruction following.
Yeah.
All while running at 17 FPS on a single H100. It's a huge leap.
Okay, let's slow down a bit and really get into the weeds here, because when we say interactive video generation, we're not just talking about making a cool clip for social media. This is, the holy grail.
We're talking about playable world models.
Exactly, like what we're seeing with Google's Genie 3 or this whole field of embodied AI. The goal isn't a movie, it's a simulator. You press a button, the world reacts instantly.
But instantly is the key word there. The bottleneck has always been latency.
I mean, anyone who's tried running a big diffusion model knows the pain. You wait seconds, maybe even minutes, for a tiny clip. You can't build a video game where the input lag is 10 seconds.
No way. So the industry standard solution has been distillation. You take a heavy hitter, like a 1, 2.1 or a Sora-style model, and you try to compress it.
Make a 50-step process into a 1-step or 4-step process.
Right, but video has this time component that images just don't. And that's where this architectural gap comes in.
Okay, so this is the crux of the whole paper.
This is it. Our best video models, the teachers, are bidirectional. They look at the whole video at once. To do noise frame number 10, they're looking at frame 1 and frame 20 at the same time.
Which is great for quality and consistency if you're just generating a file offline.
Precisely. But the student model, the interactive one, has to be autoregressive. It can only see the past. It can't know what's in frame 20 because, the user hasn't done anything yet.
So you have a teacher with this all-seeing eye trying to teach a student who's basically driving forward-looking only in the rearview mirror.
That's a perfect analogy. And methods like the old soda, self-forcing, they tried to bridge that gap. But this paper argues they were doing it in a way that's, mathematically doomed to fail.
Okay, let's talk about that math. The paper gets pretty deep into this concept of injectivity. Maybe a quick refresher for those of us who haven't touched ODEs in a while.
Sure. So diffusion is basically solving ordinary differential equations. And for distillation to work properly, the mapping has to be a function. One unique input has to map to one unique output.
That's injectivity.
That's injectivity. Now, if you're distilling a bidirectional model to another bidirectional model, you're fine. Video-level injectivity holds. One noisy video file maps to one clean video file.
But for our interactive student, we're not working with the whole video, we're working frame by frame.
Exactly. So we need frame-level injectivity. One noisy frame has to map to one unique clean frame. But remember our teacher.
It's bidirectional, it sees the future. Okay, so let's walk through an example. We're at frame 5, the student sees frames 1 to 4.
Right, and the teacher sees frames 1 to 4, and it also sees frames 6, 7, and 8. So let's say there's a ball rolling. In one possible future, at frame 8, it hits a wall and bounces left. In another, there's no wall and it just keeps rolling.
The teacher sees the wall at frame 8, so it knows how to start rendering the bounce back at frame 5.
Exactly, it uses that future context. But the student, from its perspective, the input at frame 5 is identical in both scenarios. It has no idea about the wall.
So the same noisy input at frame 5 could lead to two totally different, valid, clean outputs. One where the ball starts to turn, one where it goes straight.
And boom, you've just violated injectivity. It's a one-to-many mapping. And when you train a neural net on a one-to-many problem using something like mean squared error, What does it learn?
It learns to split the difference. It picks the average.
It learns the conditional expectation. It averages all possible futures.
So you get a blurry ball that's kind of doing both things at once, but also neither.
That's it. It collapses to the mean. This is the explanation for why so many of these real-time models look so ghostly and blurry during complex motion. The model is hedging its bets against a future it can't see, but that its teacher could.
That is such a clean explanation. It's not just a small model problem, it's a fundamental math problem.
It's a theoretical failure. You can't distill non-causal knowledge into a causal model without breaking things. You have to fix the teacher first.
Which gets us to the solution, causal forcing. So if the problem is the teacher sees too much, you have to, constrain the teacher?
That's a good way to put it. The authors say to fix this injectivity problem, the teacher must also be autoregressive.
Okay, but if you're training a new AR teacher from scratch, you have to decide how to train it. The paper spends a lot of time on this teacher forcing versus diffusion forcing debate.
Yeah, and this is where they really challenge the prevailing wisdom. A lot of recent papers have leaned very heavily into diffusion forcing.
Can you just quickly break down the difference?
Sure. Teacher forcing is the classic way. To predict the next frame, you feed the model the perfect ground truth previous frames.
Simple. And diffusion forcing.
Diffusion forcing is where you add noise to those previous frames during training. The idea is that it makes the model more robust. It learns to handle its own imperfections because at inference time, its own generated frames won't be perfect.
That sounds really smart, actually. Why would that be wrong?
It's what the paper calls a distribution mismatch. They point to Proposition 3.4. The argument is that logic sounds good, but it creates a huge gap between how you train the model and how you actually use it.
How so?
Well, think about the inference loop. The model generates a frame, cleans it up, and then that clean frame becomes part of the history for the next frame.
Right.
So at inference time, it's always looking at a clean history. But with diffusion forcing, you've trained it to expect a noisy history. You hand it a clean one, and it's kind of out of its depth. It's an out-of-distribution input.
Ah, so you made it robust to a problem that doesn't actually exist in the final application?
Exactly. The paper even says models trained this way can suffer from video collapse. The motion can become incoherent because the model is almost confused by the lack of noise it was trained to expect.
So their verdict is just keep it simple. Use teacher forcing.
Use teacher forcing. Condition on the clean ground truth frames. It just aligns training and inference perfectly.
Okay, so let's put the whole causal forcing pipeline together. Step 1 is what we just discussed.
Step 1, train an autoregressive teacher and do it with teacher forcing. No peeking into the future, no adding noise to the past.
Step 2 is the distillation itself, causal ODE distillation.
And this is the magic step. You initialize your student model from this new causal AR teacher. And because the teacher is AR, it doesn't see the future.
So frame-level injectivity is preserved.
Yes. The student and the teacher are now on a level playing field. One noisy input maps to one unique, clean output. No more averaging, no more blur. The student can learn a sharp, correct mapping from the start.
And the final step, step 3, is asymmetric DMD.
Right. Distribution matching distillation. It's a final polishing step, almost like a Jan objective, to get the textures and details looking really crisp.
But the previous method, self-forcing, also used DMD. Why didn't it work for them?
Because the order of operations is critical. Self-forcing tried to use DMD to fix a model that was already broken. They did the bad initialization from the bidirectional teacher, got a blurry student, and then hoped DMD would clean up the mess.
It's like trying to polish a blurry photo. You can make it sharper, but you can't recover the details that were never there.
You got it.
Yeah.
The paper shows that DMD cannot fix the problem if the initialization is non-injective. You have to fix the core mathematical setup first with the causal ODE step. Then you polish.
So it's not some new fancy model architecture. It's just being rigorous about the theory.
That's the whole story. Fix the teacher, fix the initialization, then polish.
All right, let's get to the results. They built this on top of a Guande 2.1 model.
Yep, a solid 1.3 billion parameter open model. And they trained it on just 3,000 synthetic videos, so it's a fair comparison against the baselines.
And using vBench for evaluation, what was the standout metric?
Oh, easily the dynamic degree. It measures how much motion is in the video.
Yeah.
Causal forcing was 19.3% higher than self-forcing.
That's not an incremental improvement. That's a huge leap.
It completely validates the theory. The old model was so uncertain it just produced static or barely moving videos to be safe. This new model is confident. It can generate real, significant motion.
But is it the right motion?
Well, that's where the instruction following metric comes in. And that was up 16.7%. So yes, the astronaut actually waves their hand. They don't just, vibrate slightly.
Okay, but the result that really jumped out at me was the comparison to the original teacher model.
Yeah, that's wild. Normally, you expect the distilled student to be faster, but a little worse than the giant teacher model.
I hear.
Causal forcing the student actually matches, or in some cases, beats the original bidirectional Guande 2.1 teacher.
How is that even possible? The student has less information.
The likely reason is that by enforcing a causal structure on the teacher in the first place, they just made a better, more temporally coherent model. It's not fighting with itself by trying to reconcile the past and the future. It just learns a more natural flow of time.
And the performance, 17 FPS, you said.
17 frames per second on 1H100. Latency of about 0.69 seconds.
That is real time. That's actually interactive speed.
It is. It's 20 to 79% higher throughput than the bidirectional models they compared against. This is what unlocks using these things for games, for simulators, for things that happen live.
And if you look at the actual video examples they provide, the difference is it's not subtle.
Not at all. The self-forcing stuff has that classic AI video look where backgrounds kind of warp and faces smear when they turn. The causal forcing videos just look solid, temporally stable.
So if we bring this all home, what's the big takeaway for an ML engineer listening to this?
For me, it's that you have to respect the math of the problem you're solving. You
Right.
can't just throw a standard teacher-student setup at a problem without thinking about the underlying assumptions. Moving from offline generation to real-time generation fundamentally changes the problem.
You have to respect the ODEs.
You have to respect the ODEs. If you violate injectivity, you're going to get blur, and no amount of extra data or compute is going to fix that. They found the theoretical flaw, fixed it, and the quality just naturally followed.
It also makes you question that whole diffusion forcing is better idea that's been floating around.
That's the thing that's really sticking with me. If teacher forcing was so much better here, and the whole robustness to noise argument was actually harmful, where else are we making that same mistake?
Right. Robotics, audio, maybe even language models.
Are we adding noise in other domains, thinking we're making things more robust, when we're actually just creating a distribution mismatch that's hurting performance? This paper makes me want to go back and check.
It's always great when a paper just says, hey, you know that simple classic method? It was actually the right one all along.
Makes you wonder what else we're overcomplicating.
Well, if you want to see the difference for yourself, and you really should, go check out the project page. The side-by-side comparisons between self-forcing and causal forcing are night and day.
Definitely do that. It's a real peek into what the next generation of interactive media could feel like.